Today's lessons is about mechanical properties of materials. And by saying the material properties, we revisit the normal stress and normal strain curve that we have in the previous lesson. So let's revisit normal stress and normal strain curve. And if you recall in the previous lesson when we talk about the normal strain curve, it represents a unique for each material and that consider footprint. So let redraw that curve. If we have x and y components in x is go with the sigma normal stress and normal strains. If you recall, that will be epsilon normal strain. And the behavior, and in this case, let select for ductile material. And originally, it will be go proportionally linear motion, and then it about to curve, and that's still elastic, and then without changing the load, increasing the load, the material start yielding, so that you can see it no load change, material still yield, so it still have the normal strain increasing. And then if we continue increase the load, then the material keep yielding. At some point they get a maximum stress. Even we reduce the stress, the material keep elongation, and at some point it will be brittle, or it will be break of the material, and that point we call it rupture. So it will be stopped in there. So there are a few components that we want to look at in this behavior, the normal stress and normal strain curve. The first portion that we call elastic, if you remember that in the previous lesson, there are elastic and inelastic or plastic region. So this portion is basically elastic. The behavior of the material in elastic. When it's elastic, it means that when you release the stress, the material will go back to the original form. And now, if we keep increase the stress, that portion go to here, it will be plastic. So when the material already in plastic or in elastic, even you release the whole stress apply on the material, then that material cannot get back to the original form, and that plastic. So last time we also defined the Young modulus is the slope, the vertical. If we go horizontal one in the normal strain, whatever sigma change vertically, normal stress change, that it is the Young modulus or the modulus of elasticity. So there are a few things that we need to talk in here. So as you can see, the material start yielding after about the elastic. So without increasing the stress, the material keep yielding, the epsilon, the normal strain keep increasing, and this portion we call it yielding. This region yielding. And then go to at some point, at peak, the region after yielding to that peak point of the maximum stress. We will call that later on. But that, as you can see, we call strain hardening. So it means we have to increase the stress so that the strain can increase. So that we call that portion is strain hardening. Strain hardening. And the final, until it rupture. So this is the rupture point, and you can see there, rupture. Between the after the strain hardening to the rupture, that we call it necking. That portion is necking. What is necking? So it's neck, right? So necking. So let's see the testing equipment that I copied from the books, as you can see on the left, and then the specimen you have to get the tensile lab. Our equipment for the lab is a little bit different that I'm going to show you in a few minutes. So as you can see, the necking is basically, it happened in that here, that finger, it necking. So you reduce when you apply the stress, increasing at certain point, it get the necking, the size of the cross section of the specimen is reducing, and as it keep increase, at some point it will have a rupture. So the material no longer work, no longer perform as intended. That is rupture, necking. And the angle, when it ruptured, the angle between the failure and the original form is about 45 degrees. And why that 45 degrees? Because the failure in this case is normally the shear stress. And if you recall the worksheet 1F, when we vary the theta from 0, theta from the transfer cut to any random cut from 0 degree to 180 degree, the maximum shear stress happen at theta equal to 45 degrees. So that is the necking in there. Our lab, just go a little bit quick here. So this is the equipment for our lab, and you can go ahead to read that instruction and to prepare for the presentation with the report for your first lab tensile tension lab instruction. This is the equipment to read, and this is to put the specimen in, and the specimen in this case is here. You measure the thickness, the initial length, that is L0, and then the width of the material in the reel. This is the specimen that you have, and with that you go ahead to read that is specimen, and after it rupture, you see that there you can measure the final length of the material to find out the L finals, and you can find out the delta, which is the deformation of the lab. So go ahead to read that one. Let's back to the class here. So that is necking, and that represent for this. So that put a few more behavior for that material here. So we grab up. So when it start yielding, and you can see the bonds between the molecule is breaking. In this case, start bonds breaking. And the molecules realize for the yielding, right? So molecule realign. And when it starts strain hardening, the realignment, complete realignment of the molecule, realignment. Complete. And when the Neckins condition, Neckins region, as you can see, we don't increase the strength, the normal strength keep increasing, and that is called local instability in that region. Local. And why local, we'll show you back to the finger in a second. Stability. So with local instability, as you can see here, it happened at one certain point locally on the specimen that you have necking and rupture in there. So now there are a few points that we need to remember for this. There are a few points in here. So as you can see, the point that the material start yielding, the point that the material start yielding, and that point with corresponding the normal stress on the vertical axis, that we call it sigma yield. And remember, like A36 steel, we have sigma yield is 36 ksi. So that is the point that have the normal stress sigma yield, then the material start yielding. And then the point just before it here, elastic region, and that sigma very close to sigma yield, that we call sigma elastic, E or EL. So if we apply the stress until sigma EL, elastic, then the and it's still in elastic behavior, the original form can be returned if the sigma is released to 0. And also in some problem in the worksheet 2, you have the proportional limit. So what does that mean? If in the linear portion, only in linear portion of that behavior, sigma and epsilon curve, that will have a proportional limit, PL. And the one that maximum stress for the material, that we call it ultimate stress. ULT or use. Okay, so and then the rupture, we don't need to define here, but in the book, that sigma here, they call sigma B breaking strength. That is, B stands for breaking strength. So with that, let's do a few points to remember in the next video. But for now, as you can see, that is the behavior, and return to different material properties. And in the next video, we will talk into detail what is sigma proportional limit, sigma elastic, etc.